or 3 minutes, maybe somebody else will join us. Okay, I think that we can start. And our today meeting, we will start with the definition of eigenvectors and eigenvalues. So it is the first topic for today, eigenvectors and eigenvalues. We will be talking a lot about applications of these two concepts. But first, we should start with a definition. Assume that we have a square matrix A. So A, it is a matrix. And this matrix may have eigenvectors and eigenvalues. A vector V is called an eigenvector of this square matrix A if it satisfies this condition, which you see here. A multiplied by V is equal to lambda multiplied by V. Then V, it is an eigenvector, and lambda, it is a scalar, it is a numerical value, it is an eigenvalue. So this is a definition. We can say that V is an eigenvector of a matrix A if it satisfies this equation, this formula. And then lambda is called an eigenvalue. Of course, we can calculate, we can compute eigenvectors. We have a matrix here. This program, the results of this program we see here. I define the matrix. It is a matrix P, very small matrix with 2 rows and 2 columns. And here, in this line, I use eig function for calculating eigenvalues and eigenvectors. And these elements, eigenvectors and eigenvalues, are here as W and V. In W, it is a vector. We have eigenvalues, and V, it is a matrix in which we have eigenvectors. And I displayed these two objects here, eigenvalues V and eigenvectors, eigenvalues W and eigenvectors V. So we see eigenvalues here, and it is a matrix with eigenvectors. But we should remember that eigenvectors we have in columns of this matrix. So the first eigenvector, it is the first column, not the first row, but the first column of this matrix. So first eigenvector is here. The second is here. So we have 2 eigenvalues and 2 eigenvectors. This first column, it is an eigenvector which is related to the first eigenvalue. In the second column, we have the second eigenvector, which is related to the second eigenvalue. So we can calculate eigenvectors and eigenvalues with no problems. We have a function which we can use. So we know the definition. We know how to calculate them. But for us, I think it is very important how to interpret them. Please look at this program. In V, you remember, we have eigenvectors. In the first column, we have the first eigenvector. So I get this first eigenvector, all elements from all rows and from the first column. Because we prepared it in Python, we know that in Python, the first column has a number 0. So the first eigenvector is printed here, and we see this eigenvector. And I draw this eigenvector. It is here. It is here, this red vector, it is the first eigenvector. And here I calculated a vector W1. It is a transformation of the first eigenvector, and the definition of this transformation we have in the matrix P. It is a matrix for which we calculated eigenvectors, because this matrix P was defined here. So I transform the first eigenvector using this transformation P. And I obtained a vector W1. And this vector W1 is here presented in blue. So red, it is an eigenvector, and we transformed this eigenvector. We remember, when we are talking about transformation, about linear transformation, we are talking about multiplication by a matrix in which this transformation is defined. And the result is here. I calculated lengths of these two vectors. In the first and in the second case, it is the same. Practically, it is equal to 1. But it is very interesting that these two vectors, so this eigenvector and its transformation, the transform vector, lies on the same line. We can say that they have the same direction. And it is always true for eigenvectors, that eigenvectors for a given matrix P, after transformation in which we use this matrix P, will produce vectors which lies on the same line. So we see that this red vector was transformed, was changed in this transformation in a way which was defined in P matrix, but this modification is not very big. Because here in this example, the result which we obtained lies on the same line. And in this case, also the length of this vector which was produced is the same, because it is equal to 1. So eigenvector means vector which has very good relationships with a matrix for which it was calculated. Why I said that this vector has a very good relationships? Because during a transformation, which is defined in this matrix, the changes which are made to this vector are very small. Because the result, it is a vector which is located on the same line. So the direction of this vector is the same. Also, we can check it with our second eigenvector. The second eigenvector is here, V2. It is the second column from the matrix V. We see this eigenvector here, and I transformed it. It means I multiplied it by a matrix P, and I obtain vector W2. And I draw these two vectors. This eigenvector, V2, and vector which I obtained as a result of this transformation. And these vectors are here. The original vector is here. It is this red one, so it started in point 0, 0 and ends here. And the result, it means W2 vector, is here. It is this blue vector. So it is longer, because the length of the first is equal to 1, the second, this blue, the length is equal to 4. So its length is 4 times greater, bigger. But also we see the same regularity, that the eigenvector and its transformation lies on the same line. Of course, it is, I think, now obvious for us, but also we can say that it should be obvious after seeing this definition of eigenvectors. Because as I said before, V, it is an eigenvector of A if A multiplied by V is equal lambda multiplied by V. On the left side, we have a product of a matrix A and a vector V, and the vector V. It may be interpreted as a transformation of vector V, where A, it is a definition of this transformation, which has a form of a matrix transformation, of a transformation matrix. So I transformed this V vector using a transformation which was defined in matrix A. And the result is here. It is vector V multiplied by lambda. It is a multiplication of a vector by a scalar value. When we are talking about this form of multiplication, we know that the result lies on the same line. It may be longer or shorter. It depends on the value lambda. So we see that the transformation of of V vector and multiplication by a lambda gives the same result. So we see here that how it works. But also, I would like to interpret eigenvalues. -1 and 4. For the first case, it was -1. Eigenvalues inform us about the relationship between lengths of an eigenvector and its transformation, which was defined in the matrix A. So here, we have that the length was the same, but heads of these arrows are directed in opposite sides. So therefore, we have -1. -1 means that these two vectors lies on the same line, but are headed in opposite directions. The second eigenvalue is 4. We had it here, it is 4. So it means that for the second eigenvector, we just plus 4. So it means that eigenvector and the result of the transformation are headed in the same direction. And that the result of this transformation is longer than an eigenvector, 4 times. We see it on this picture. So now we know how to interpret eigenvectors and eigenvalues. Eigenvectors, it is a group of specific vectors which are defined for a given matrix, because they can be defined only in the context of a given matrix. And these vectors are transformed by this matrix in a very friendly way. This transformation does not change the direction. It may change only the lengths of these vectors, and also vectors which we obtain may be headed in the opposite direction. Sometimes they are headed in the same direction, sometimes in the opposite direction. So it is a concept of eigenvectors. And this concept is very, very useful in data analysis. And today also I will use this concept many times. The next issue, which is also very important in mathematics, but also in linear algebra. It is the problem of solving of systems of linear equations. I think that you met this problem many times. Here we see an example. We have a system of linear equations. Here we have 3 equations with 3 unknown values, parameters, x1, x2, and x3. So we see what relations are defined between x1, x2, and x3. All these relations are defined as linear combinations. So we have linear equations, 3 equations with 3 unknown values, with 3 unknown parameters. And we want to solve it. And I think that in your primary, maybe in secondary school, you try to solve these systems. Also, we can use Python for it. So, for example, if we have a problem like this problem, we can define it using 1 vector and 1 matrix. And here we see the definition of this task in this program. So here, A, it is a matrix of coefficients which we have on the left side of every equation. On the first matrix, on the first equation, we have coefficients 4, 3, minus 5. And these values see here, 4, 3, minus 5. In the second equation, -2, -4, 5. It is the second row of this matrix. And here we have 8, 8, and 0, because for x 3, we have a parameter which is equal to 0, coefficient equal to 0. So we have these values here. And in this vector y, we have these values which we have on the right side of every equation. These values are called constant values. 2, 5, minus 3. So parameters of our task we defined here. And if we want to solve this system of equations, we should use solve function. We should use solve function, and the 2 parameters are necessary. The first, it is an A matrix with values which we have here. And the second parameter, it is a vector with constant values. And the result is produced, and the result was assigned here to X object, and I printed it. And the result is here. So I solved this system of linear equations. You see that it is very, very simple. So in practice, we can use this approach. I think that some of you know how to solve it manually. We can, because you know it is necessary to calculate the inversion of this matrix and multiply it by this vector. That's all. But of course, in practice, you can use this function. But we have a very interesting problem here. Because here, I solved this system of equations with no problems. But sometimes we can get the information that the solution does not exist. Or sometimes we can get the information that we have an infinitive number of solutions. So we see that there are different situations, different cases. And how to answer the question, if it is possible to solve this system of equations or if it is not possible. And if it is possible, what we should do to solve it. So we have this system of linear equation, which is defined in this form. It is a matrix form, but of course the interpretation is the same. So here we have a matrix with coefficients, here a vector with unknown parameters, and here constant values. And x, as I said before, is equal to a, the inversion of a, multiplied by b. But not always it is possible to solve this system of equations. If we want to check if it is possible or not, we should create the augmented matrix. This matrix is here. Name maybe this matrix may be strange, but it is a very simple construction. It is a matrix A, and we should add on the right side of this matrix vector B. So here we see, we will see the example. So we have this augmented matrix, and we can check the rank of original matrix and the rank of this augmented matrix. And we should compare these 2 values. With the rank of A matrix is not equal to the rank of this matrix in which we have A and vector B, this augmented matrix, then there is no solution. So in this case, when these ranks are not equal to each other, there is no solution. If ranks of these two matrices are equal to each other, and these ranks are equal to n, and number it is n it is a number of unknown parameters, variables, then we have only one solution, unique solution. So in this case, we had only one solution. If these ranks are equal to each other, but if the rank of A matrix or augmented A matrix is smaller than n, then we have an infinitive number of solutions. And how to use these rules? We have a system of three equations. Here it is defined. It is represented in this program by this A matrix. It is vector B with 3, 4, 6 with these constant parameters. So we see matrix A here, vector B here. Augmented matrix, this extended matrix, we can say. It is matrix A to which we added one column, and values which we have in this column, the last column, the fourth column, are equal to vector B, 3, 4, 6, 3, 4, 6. So we have all data which are necessary if we want to answer the question, if it is possible to find a solution of this system of equations. So it is necessary first to calculate the rank of A matrix. You remember the definition of rank. It is a number of columns or rows which are linearly independent. So for this matrix, it is 3. Here, for A matrix. For augmented matrix, for this extended matrix, so A plus this one extra column B, also it is 3. 3 is equal to the number of unknown variables, because here in this system we have x, y, z. So it is 3 here, it is 3 here, and it is, and also we have 3 unknowns. It means that this system has one solution, and it is possible to solve it using this formula, this function solve, this method solve. So everything was calculated here. So these topics which are related to systems of linear equations also are very popular in linear algebra, and we see that in very, very simple way we can solve these systems, but we should remember that before solving it, we should check the existence and number of solutions. And the way in which we can do it from a practical situation, we see here, using programs which are very similar to this program. And the last issue, which I wanted to discuss in this first part of our lecture. It is a concept of basis. You remember, we were talking about vector spaces. And in vector spaces, we have vectors and also definitions of two operations. We have a definition of multiplication by a scalar value and addition of two vectors. And using these two operations, we can define a set of vectors, which is called the basis for this vector space. A set of vectors. In this example, we have these two vectors, this red one and this blue one, which can be used for generating any vector which you have in this vector space. So it is possible to create any vector. For example, I'm going to use these two vectors for creating this green vector. What should I do? First, I should multiply this vector, this blue one, by -2. When I multiply it by -2, I will get a vector starting in 0, 0 point, and which ends here in -2, 0 point, this vector. And after it, I can add this vector which was generated and this red vector. And in this way, I can obtain this green vector. So always it is possible to find a sequence of operations which I should perform on these vectors which create the basis for this vector space, to build, to generate, to create any vector which may exist in the space. This basis, which I have here, is called a standard basis, because coordinates of these vectors have a form which we see here. 0 values, and in the first vector we have 1 on the first position, and in the second version we have 1 on the second position. When we are talking about three-dimensional space, then the basis is here. It is a set of these three vectors, is red, blue, and green. And also using these operations, which I mentioned before, multiplication by a scalar and addition, I can generate any vector in the space, in this three-dimensional space. So it is a basis. So it is a basis, and the standard basis for three-dimensional space is here. These vectors are defined in this way. The same operation we can perform for four-dimensional space and for n-dimensional space, generally speaking. But in this case, in every case, we will have as unit vectors with values equal to 0 and with one value which is on the first, on the second, and in the last vector on the last position. So it is a set of a standard basis. And we use automatically this standard basis. So if you want to define the coordinates for this green vector here, I may say -2, 1. It means these values, these coordinates, of course, these coordinates define a point in which this vector is ended. But also we can say that these coordinates also inform us about operations which we should perform on unit vectors, which form the basis for this space. I should the first vector multiply this horizontal unit vector by -2, and this vector I should multiply by 1, this operation has no impact on this vector. And after that, I should perform the addition operation of these two vectors. And I will obtain this green vector. So we use this basis very, very often. Automatically, and I think that when we are talking about vectors in a vector space, we know about all these issues, but we don't think about it. But we should also remember that we can have many bases. For example, here on this graph, you see this standard basis. It is defined by these two unit vectors, this blue one, but also these vectors which we have here, these two red vectors, can be used as a basis. Also, it is possible to generate any vector which we have in this vector space by performing these two operations, multiplication by scalar and addition of vectors, using at starting point these two red vectors. So it is possible. We can do it for and generate any vectors. So we can have an infinitive number of different bases. Sometimes it is useful to change the basis, to move from one basis to another, and to express the location of some objects, some other vectors, some points in different bases. So here we see two bases. This blue, it is a standard basis, and this new basis, which is here represented by these two red arrows. This graph was generated using this program. And now, the most important element of it, how to change bases, how to move from one basis to another. So we have a vector, and this vector is defined, its location is defined using this standard basis. For example, it is the situation which we have which we had here. This green vector, its location is defined in the context of this basis, which is created by these two unit vectors. And now, remember, we have a new basis. So also it would be possible to draw these two vectors which form this new basis here. And we want to define the location of this green vector, but in the context of this new basis. No, in the context of these unit vectors which we have here, but in the new basis. How to calculate coordinates of a vector in a new basis. So we have a vector which we have in the standard basis. This vector is here. So we have a vector with coordinates 2 and 2. So this vector we can draw here from this point 0, 0 to point 2, 2. So this vector which should be drawn here, it is a vector which we have in this standard basis. And I'm asking you about the position of this vector in this new basis. So please imagine that we have a new coordinate system with x and y axes. And x-axis is here. This red arrow, it is an x-axis, and y is here. Please look at this angle. These axes are not perpendicular. But sometimes we can have coordinate systems with non-perpendicular axes. And we want to express the position of this vector in this new coordinating system. We should remember about this very important for us expression. This rule which we can use and transform it to when we want to change the basis. So we have a vector, V vector. To say the truth, it is Vs. It means that these coordinates are defined in the context of a basis S, the standard basis. So as it is a standard basis, it is here. So we have the definition here, 1, 0, 0, 1. So it is a standard basis. This is blue 1. And in this basis, we have a vector with coordinates 2, 2. And here I displayed these coordinates here. And here on this equation, on the left side, we have a product, S multiplied by Vs. Vs, it is a definition of this vector with respect to this basis S. So we have here this vector 2, 2, and S, it is this standard basis. It is this matrix, 1, 0, 0, 1. So these elements we have here. On the right side, we have very similar elements. Also, a product of two elements, B and VB. B, it is this new basis, this red one, which is here. And VB, it is a vector, the same vector which we have here, but with coordinates which are expressed with respect to the basis B. And it is always true that these two products generates the same vector. It is always true. So if we know S, it means a standard basis. This new basis B, also we know it. It is here. So we have this basis. We have this basis here. This matrix. But we should remember that the first column, it is the definition of the first vector, and the second column, it is the definition of the second vector. So also these vectors which form this basis, we have in columns of this B matrix. So we know B, and we want to calculate this vector VB. It means coordinates of this vector with respect to the basis B. How to calculate it? We should multiply both sides of this equation by the inversion of the B matrix. And then we have inversion of B multiplied by S, but S, it is a unit matrix. So the result of this multiplication is equal to minus b. Multiply by Vs. And on the right side, we will have inversion of b multiplied by b. We know that in this way, we should produce the identity matrix. And therefore, we have VB here. So changing these two sides of this equation, we see that we can express coordinates of this VB vector using this formula. And here, having this vector Vs, I calculated coordinates for VB vector here. So inversion of B multiplied by Vs. It is this equation is used here in this program. And coordinates of this vector Vs with respect to the basis B is here. So we see the position of this vector from the point of view of the basis B. So we change this basis. If we have a situation in which we knew the position of this vector of, if we know this VB vector and we want to express this vector in the standard basis, then also it is possible to obtain the correct formula for it. So we see how it works, and you see that it is not difficult to change the basis. But of course, I think the most important element here is to know what this concept, the basis, means. But the interpretation we see is very, very easy. It is a set of the minimal set of vectors which we can use for producing any vector in a given vector space. So now I think we can move to the second part of our today meeting. Do you have a short break now, or maybe later? So maybe I will talk about this topic, eigendecomposition of a symmetric matrix, and after it, we will make a short break. So we know the concept of eigenvectors. We know how to interpret them, how to draw them, how to use them, but also they are very important when we are talking about decomposition problem. In many situations, in data analysis and in mathematics in general, we are talking about the decomposition. Decomposition means that we are going to decompose something into simpler parts. In the context of linear algebra, it means that I'm going to present something as a product of other elements. So decompose, it means to present something as a product of other elements. And we are talking about decomposition very often when we are talking about different matrices. For example, when we are talking about the composition of matrices, then we are talking about the problem in which we are going to present this matrix as a product of other matrices. For example, matrix A here we present it as a product of three matrices. It is a decomposition. But now we are talking about the decomposition of symmetric matrices. Symmetric means that above and below the main diagonal, on the opposite side of main diagonal, we have the same values. And in this decomposition, we will use eigenvectors. So please look at this formula. We can assume that we have a matrix A. It is a square symmetric matrix. Square symmetric matrix, for example, this matrix, is a square symmetric matrix. On the main diagonal, we have values 3 and 7, and on the opposite side of this main diagonal, we have the same values, 1, and value which is located on the opposite side of this main diagonal is also equal to 1. It is very small matrix, but we see we can see here this concept of symmetric matrices. So we are talking only about the decomposition of this type of matrices. Some elements which will be discussed here may be much more complicated when these matrices which we are going to decompose are not symmetric. So we are talking about only about symmetric matrices. Of course, in other types of decomposition, also we can decompose matrices which are not symmetric. But here, when we are talking about eigendecomposition, it means the decomposition in which we use eigenvectors, it is limited only to this type of matrices. But it will be enough for our application. So we have this matrix A. And first I calculated eigenvectors. I know how to do it. There is in Python function eig, and I use it for calculating eigenvectors and eigenvalues. And this A, it is eigenvector matrix. In every column of this matrix, we have one eigenvector. And D, it is a matrix in which we have eigenvalues on the main diagonal. But elements which are not on the main diagonal, all of them are equal to 0. So we have eigenvalues on the main diagonal and other values outside the main diagonal. And we can say that matrix A can be reconstructed, can be expressed in this form which we have here. So we can make, we can take E matrix with eigenvectors, multiply this matrix by D, and the result we should multiply by matrix E, but after transposition. Transposed E here we have. And for every symmetric square matrix, it is true that we can present this matrix in this way. We can check it. I have this matrix A here defined. It is small matrix, but of course we can check that for matrix with more rows and columns also it is possible. Also it is true. I defined this matrix here. This matrix is here. I performed this. I calculated these eigenvectors and eigenvalues. But we should remember eigenvalues. Eigenvalues are here. Eigenvalues are here. So I displayed it, and the result is here. It is a vector with eigenvalues. But in this formula, in this expression, we have D matrix. D matrix, it is a diagonal matrix. So it has eigenvalues on the main diagonal and 0 values on all other positions. How to create this matrix? I created it here. So eigenvalues, so this vector with eigenvalues I use here, and I produce a matrix D, and this matrix D is here. So on the main diagonal, we have these eigenvalues. This value is here, and this value is here. And on other positions, we have values equal to 0. So it is this matrix D. I printed it here. And it is a matrix with eigenvectors. It is not necessary to perform any operations on this matrix which we obtained here. So this matrix A is here. And now I would like to calculate the value of this expression, E multiplied by D multiplied by E after transposition. And this is here. This expression is here defined. E multiplied by D, and transposition also we can define in this way. Because you remember, during our last meeting, I show you that we can use a function which we have in Python, but also this notation is allowed. So instead of this function, we can use this notation dot and letter T. If we add these two elements, dot T, after a matrix or a vector, it means that I want to perform the operation of transposition, the transposition operation. So I calculated the result here, and I displayed it here. And this matrix which we have at the end is presented here. Please check that this matrix is equal to this matrix which we have at the beginning, 3, 1, 1, 7. Of course, the type of elements is different, because here it was a matrix with integer values, because these matrices, and these matrices, we have real values, not integer values. Therefore, the result also is presented in this form, with real values, not with integer values. But we see that values are the same. So it is a theorem about the decomposition with the use of eigenvectors and eigenvalues. Therefore, it is called eigendecomposition. And here we see the very short program in which I use this formula. But I think that we should talk about one element in this program. Here I calculated eigenvalues and eigenvectors. Eigenvalues are here and eigenvectors are here. Of course, eigenvectors are assigned to eigenvalues which are on the same position. We know about all these aspects. But there is one issue which we did not discuss. The order of eigenvalues. Here we obtain two eigenvalues. The first is equal to 2.76 and the second 7.23. So they are in ascending order. The second one is greater. Of course, everything is okay, but it will be better for us to have eigenvalues in descending order. So I want to have the biggest value here on the first position. The second value should be smaller than the first. The third should be smaller than the second, and so on. So I would prefer to have eigenvalues in descending order. Of course, there is no problem with changing, because we can sort them. But also we should remember that after changing the order of eigenvalues, we should change in the same way the order of columns in a matrix in which we have eigenvectors. Because we don't want to change the way in which eigenvectors are assigned to eigenvalues. And in many programs, for example in R, but also in other packages, when we generate eigenvalues, they are always printed in descending order, but not in Python. And we should, I think, improve it, and we should add some parts to our program, some lines, which we have here. It is for sorting eigenvalues. So here eigenvalues were sorted. So I got positions of elements with respect to their value. They were sorted, and I reversed their order by putting -1 here. And eigenvalues, I change the order of eigenvalues using these indices, and also change the order of columns in a matrix with eigenvector. So it is here. So I use this modification in my program, and now we see the result. So the input matrix, starting point for our calculations is here. It is the same matrix. Eigenvalues we have here in descending order. So the biggest one is on the first position. And also I change the order of eigenvectors, because I did not want to change the way in which they were assigned to eigenvalues. So to this first eigenvalue, which is equal to 7.23, this vector, this first eigenvector is assigned minus 0.22 minus 0.97. And here also, to this eigenvalue 7.23, the same eigenvector was assigned. So I change the order of elements here, and in the same way, I change the order of columns here. And now we have eigenvalues in descending order. And it may be very, very helpful. Maybe for this application which we have here, it is not a crucial thing, but in some applications it may be very, very important. But also for us, we will see that in some minutes it will be very useful that we will have eigenvalues sorted in this order. So now I would like to make a short break, maybe 8 minutes, and 15 minutes past 5, we will continue. Okay, so we can continue. And first about orthonormality. About orthonormality of vectors, but we will be talking about orthonormality of columns of a matrix. Orthonormal means perpendicular. So if two vectors are orthonormal, it means that they are perpendicular. And you remember, when we have two vectors perpendicular, then the scalar product is equal to 0. So if we have columns in our matrix and vectors which we have in every column are orthonormal, it means perpendicular, it means that the scalar products are always equal to 0. So when we calculate this product of these two matrices, V matrix here with these columns, and here it is transposed version of this V matrix, then as a result, we should obtain a matrix which we have 0 on all positions except the main diagonal. If we have this result, it means that columns are perpendicular, are orthogonal. But here we have also this second element, normality, normal, orthonormal. Normal means that the length of every vector is equal to 1. How to check it? You remember this formula which we use for calculating vectors' length. This formula which is based on Pythagoras law, rule. In practice, it means that when we calculate a scalar dot of a given vector and the same vector, so if we multiply the vector by itself, we should get value which is equal to 1. So if we have a matrix in which columns are orthonormal, it means that after calculating this product which we have here, the result will have this form. Values equal to 0 in this matrix except of main diagonal. And on the main diagonal, we have values equal to 1. So it is the concept of orthonormality. But when we are talking about it, we can say, as I said here, that if we have in A matrix columns which are orthonormal, then this product, A after transposition multiplied by A, is equal to identity matrix. But I think that you remember very similar rule. When we are talking about inversion of a given matrix, also we remember that matrix after inversion multiplied by original matrix also gives identity matrix. We can compare these two rules, and we can say that for matrices in which we have orthonormal columns, matrix after transposition is equal to the matrix which we can obtain after inversion. So always this rule is satisfied. Inversion of a matrix is equal to the transposition of this matrix. but it is true only if in this A matrix we have columns which are orthonormal. So also we will use this rule in some practical applications. You remember our matrix with eigenvectors. Please check this product. E, it is a matrix with eigenvectors, and we multiplied the transposition of this matrix by this matrix. And the result is here. We see values equal to 1 on the main diagonal, and elements which are out of this main diagonal are equal to 0. We discussed it 2 days ago, that these values practically are equal to 0. So matrix with eigenvectors is orthonormal. It is orthonormal matrix. And we will use this regularity in future. And in this case, we will be able to replace the inversion of this matrix by its transposition. It makes all calculations easier. So I think that now we know all basic concepts which are necessary to talk about principal component analysis. Principal component analysis, it is a method which we use in data analysis for reduction of the number of variables which we use for describing objects. And from practical point of view, it is very easy. We can use only one function and to send the original data set to this function, and we will obtain coordinates of every object, but in different bases. We will produce new variables which we can use for describing our original objects. And it will be very important that the number of variables which will be produced will be smaller than the original number of variables. It is the idea of principal component analysis, to change the original set of variables into a new set with smaller number of variables. Why it is very useful? Because when we have objects which are described by many variables, then they are difficult to analyze. They are very difficult to represent in graphical form. It is easier to present them when they are described by only 2 variables. Then it is possible to prepare a graphical presentation and to represent every object as a point. When we have 10 or 20 variables, it is not possible. So all these problems we can try to solve using principal component analysis. I noticed that you had some lectures about graphical presentation, data graphical presentation. So I think that you use some methods for reduction of the number of variables. But principal component analysis has very interesting mathematical background. And about these elements, I'm going to say some words today about mathematical foundations of principal component analysis. Because in the case of principal component analysis, but also in the case of all other methods which we use in data science, in artificial intelligence. This mathematical background is very, very important. But of course, I'm going to talk about some intuitions which are related to these problems. And therefore, also I'm going to use an example, which I hope will be useful for presenting some problems related to principal component analysis. So I have a small data set, which is composed of these points, 1, 2, 3, 4, 5, 10 points, I think, here I have. So every point, it is an object in our analysis. Every object is represented, is defined by two coordinates. So we can think about these objects as about vectors in two-dimensional space. They are here, these objects, and every column of this table we can treat as one object. And I presented them graphically. We can see them here. They are here. This program I use for producing this plot. We have this data defined here, and here I created this graphical presentation. So I have this data set. And I'm going to show you how to use some mathematical rules for analyzing this data set. We know that every object is defined by two coordinates. These two coordinates are assigned to two variables, which are here represented by axis axis x and y. And very often we can consider a problem of variables importance. Which variable, x and y, is more important here? And we said many times that the amount of information which we have in a given variable may be measured by its variance or standard deviation. Some of you who participated in my previous lecture today remember it. So this variance or this standard deviation is defined here. It is defined in this way. We can calculate variance for x coordinates and y coordinates. And variance is a measure of the amount of information which we have in a given variable. Of course, we want to have variables with huge amount of information in them, but not always it is possible. So we can calculate variances for x and y coordinates. And here I will try to do it. There is a function var, which we can use for this matrix. But I will show you how to use it for different situations. And we should choose the right way in which we want to use it, this var function. Because you remember, in this matrix XORG, we have this data which we are going to analyze. And we can put this data here as a parameter of this var function and print a value which was calculated here. This value is here. It is a variance calculated for all values in the first and in the second row. So if we want to calculate variances for every column or for every row, we should inform this function var about it. When we are talking about columns, then you should define it in this way. X is equal to 0. 0 axis means that I'm thinking about columns. When I'm thinking about rows, then I should put this information here. X is equal to 1. And then this value, it is a variance for first variable, which is in our matrix in the first row, is represented by the first row. And this is a variance for the second row. I use this parameter keep dims here because I want to have a matrix with variances, not a vector. Therefore, I wanted to keep dimensions. So here I calculated variances. Variances, it is a measure of dispersion, and it is calculated separately for every variable. Here we calculated it for the first and for the second, and because I said that it is a measure of the amount of information, so we see that the second coordinate is much more important than the first one. Also, I calculated covariances. Covariances are calculated in this way. Covariance value describes the relationships between values of two variables. It is the formula here. Here we have the sum of products of differences between a value which we have on the I position and the mean value calculated for a given variable, here and here. So we try to add these products. These products can be positive, negative, or equal to 0. They are positive when the increase of the first variable corresponds to the increase of the second variable, or the decrease of the first corresponds to the decrease of the second. Then the product of these two elements is equal to positive value. So changes are in the same direction. The first value is bigger and the second value also is bigger. If changes go into opposite directions, then these products are negative. If one value is bigger and the second is smaller, then the product is here negative. And after it, we calculate an average value for this information about the changes, about the directions of changes. So this function, cov function, produces this matrix. This matrix is called variance-covariance matrix. And on the main diagonal, we have variances. So please look at these values. This value and this value. They are equal to this value and this value. So these values here are variances. This matrix is symmetric, and these values are the same. These values are called covariances. It is a covariance between the first and the second variable. it is positive. It is positive. It means that these two variables, values of these two variables, are correlated. And if the value of the first variable is greater, then also the second is greater. If the first is smaller, then also the second is smaller. In the case in which we have negative value here, then we have changes in opposite directions. In the value of the first variable is bigger than the value of the second variable is smaller. But here, in this case, covariances are positive. So we see that these values are correlated. We see it on this picture. Please look at this picture. These points are located along the line which have such direction. So for bigger values of x, also we have bigger values of y. So this conclusion, which we can draw after looking at this picture, also we can define when we analyze elements which we have in this variance-covariance matrix. So it is variance-covariance matrix define our data. Please look at this operation. It is a centering operation. We have a data set. It is not this data set which we have because I found this picture on the internet. So we have a data set here. And data centering, it is the operation in which we are going to move all points in this way that the point which is in the middle of this data set will be located in the point 0, 0. So also we can define this operation as an operation in which we try to move our coordinate system. And the origin of our coordinate system we are going to put in the point in which is located in the middle of this data set. So this point 0, 0, we are going to move into this place, 0, 0. And the result is here. So it is very simple operation. But now I'm going to show you the impact which this operation has on variances and on covariances. And now we can say that this operation has no impact on variances and on covariances. So here we have this original data set, and I perform this centering operation. It means that I subtract average value for the first and for the second coordinate with coordinates of every point. It is defined here. Means value are here. Mean function I use for calculating average value for the first row and for the second row of this matrix. And I subtract these mean values from elements which you have in this matrix. And I presented these points graphically. So the original data set, this original data, are here as blue points. They are presented as blue points. And after transformation, I presented them again as these red points. So now the point 0, 0 is in the middle of this data set. So for example, these 2 points were transformed to here, these 2 points to here. For every point, we can find an element to which it was transformed. And I calculated variance-covariance matrix for original data and for data after transformation. It is here. It is for original data, here for data after transformation. And these 2 matrices we see here. It is a variance-covariance matrix for original data. It is variance-covariance matrix for data after centering. The same values we have. So we see that centering operation has no impact on variances and on covariances. So therefore, because we will use the information about variances and covariances in our analysis, first, having the original data set, I will center it because it has no impact on variance-covariance matrix, but it makes easier to perform calculations. So I have a data set which is centered in the origin of a coordinate system. So we have this situation. And now, using this data, I'm going to use principal component analysis. Principal component analysis. The main idea of principal component analysis is to build a new coordinate system, which also has its origin in the point 0, 0. So this new coordinate system is here presented using these red arrows. So I'm going to build it. I'm going to construct this new coordinate system. But I'm going to create a new coordinate system in a very specific way. I'm going to realize some conditions. First, the amount of information, which is measured by variances, represented by every axis, should be maximized and ordered or sorted. It means that I'm going to find the position for this first axis of the new coordinate system in this way, for which the variance which will be calculated using these coordinates of these points on this way will be the biggest one. So I'm going to maximize the variance. And ordered it or sorted it, it means that in the multidimensional case, when we have many axes, I'm going to have the biggest value of variance for the first axis, smaller for the second, smaller than for the second, for the third, and so on. So I'm going to have these variances which are assigned to every axis to be sorted in descending order. I want to have them sorted, maximized, and sorted. So it is my first goal. I want to maximize variances. I know variance, it is a measure of information. So I'm going to maximize the amount of information which I have about my points. It is the first goal. And I'm going to remove redundancy. of information represented by every axis. So I want to have coordinates non-correlated. All these goals are represented by some specific features of a variance-covariance matrix. So I'm going to have variances as huge as possible, as big as possible, and I'm going to have all covariances equal to 0. So it is my goal. It is the goal of my calculations. So I'm going to find such new coordinate system for which, when I use this new coordinate system for getting the information about the position of every point, and for these new coordinates, I can obtain variance-covariance matrix in which elements on the main diagonal should be maximized, and elements outside of the main diagonal should be equal to 0. And to do it, I should find these two axes. In this case, two axes, because now we are talking about two-dimensional space. In general case, of course, the number of dimensions may be higher. How to find the location for these two axes for which variances will be maximized and sorted and covariances will be equal to 0. So first, we are talking about finding the position for the first axis. I know that this first axis should intersect 0, 0 point. But I should find the right angle, the right position for this line. We can see it here. Point 0, 0 is here. And we are going to find the optimal position for this axis. Which position is the best one? And what we should do to choose the best position for this x-axis. Please look at this data set. This data set is represented here by these blue points. We see that these points are after centering operation. So the centroid, the center point, the mean point of this data set is in the point 0, 0. And the first axis also should cross this point 0, 0. We try to rotate them and to find the optimal position. We see these red points on this line, on this axis. These red points represent projections of these blue objects which we have. And we should analyze the position of these projections. We should find such position for this axis in which variance calculated for these projections is the biggest, because we want to maximize the amount of information which is represented by this axis. The amount of information represented by this axis, it is the variance calculated for projections, for these red points. And we should find this position for which the variance means dispersion along mean value, when this variance is the biggest. And we see that this variance will be biggest now. It was the optimal position. So this position here is the optimal position, because variance means that distances between projections of these points and mean point, which we have here in 0, 0 point, is the biggest. So in this way, we can choose the position for the first axis. We see how to do it, how to interpret it, how to do it using this picture, but how to calculate it in practice. We can consider different positions of this axis. Let's assume that we have a vector, for example, vector D here, and we know how to draw a vector. And we can assume that this line which we have here, it is a direction of this vector. Direction, it means that it is the line on which this vector is located. And we have points, and we want to calculate projections of these points on this vector. So we should define a transformation, linear transformation, which allows us to put these points on this line. It means to calculate these projections. And this transformation is defined here. When we have B vector, and if we want to project points, to find projections of points on a line which is defined by this B vector, then we should use transformation which is defined here. Here this vector is represented by D. And I created this projection matrix. This projection matrix is here. And I have my data set here after centering operation. And I transformed it using this transformation matrix P, which was defined here. This matrix was defined using this formula. And I plotted these points. So we see original points are here represented by these red points. Their projections are blue. So, of course, I did not draw a line here, but we see that these blue points are located on a line. On a line, and this line, it is a line which is defined, which may be defined as a direction of this vector 4, 1. Please look that we have so here this vector and these projections are here. For 1, it means that for 4 we have 1. For 20 we have 5. We see that on this direction we have this line, and I found projections. But of course, I know that this line, which I used for producing these projections, is not optimal, because as we saw here, here in this example, in my example, I defined the position of this vector. I know that I should find this position in this way for which the direction of this vector will be a direction for which the variance will be maximized, maximal. So I'm going to find a direction with maximal variance. It is my goal, because I'm going to find the position for the first axis. So I'm going to perform operations, to perform transformation of my original data set X to this new data set Y, using this transformation definition, which has a form of this matrix B transposed. But this B, it is a matrix with columns which we have here. When we are talking about the first, when we are talking about the first axis, so we are thinking only about first coordinates of these points, because on this first axis we have first coordinates, and they are defined in this way. So we use this first column from this matrix B, and we should multiply by every column of this matrix X, and in this way we can find positions of the first coordinate of every point from our data set on this axis. For an object which is identified by I, the result is here. And we are going to find this optimal position. We are going to find this optimal position. It means that optimal, it means it is a position for which the variance is the biggest. Variance of these projections is defined here. Why? It is the first coordinate of points on this on this first axis. So I can calculate variance using this formula. You remember that it is different formula from this general which we saw, because we had minus average value, but data are here centered using 0 point. So mean value is equal to 0. Therefore, I omitted this value. And variance can be presented in this form. So variance can be presented in this form. We can replace this Y by this element. So we can get this notation. It is a squared value. So we can put it twice here. We can change the order of elements, and we can obtain this expression. But please look at this element which we have here. It is a variance-covariance matrix, but for original data. It is S matrix. So S, it is a variance-covariance matrix for original data. So we see that variance for projections of points on this new axis can be presented in this way. We want to have this variance as big as possible. So we want to maximize this value. We want to maximize this value, but also we should remember that the length of this B should be equal to 1. B, it is a column of this B matrix, B1. It is a column. You remember, we talked about orthonormality. And then I told you that orthonormal means that it is perpendicular and the length is equal to 1. And I want to have such vectors here. Therefore, I want to have the length of this vector equal to 1. So I'm going to solve this optimization problem. I'm going to find B, parameters of B, in this way, for which we will get the variance as high as possible. And also I want to have all coordinates in this B vector calculated in this way that the length of this vector is equal to 1. So I should to solve this problem. Maybe some of you know the method which we can use for solving this type of optimization problem. Maybe tomorrow we will be talking about some elements which will be similar to it, but not the same. But when we want to, the general rule here is simple. When we want to solve problems which are similar to this problem, we should use a specific method which is called Lagrangian method. And using this method, in which we are going to find parameters for which a criterion function will have the biggest value, and in which we have one constraint, one additional condition, then it is necessary to define a function. This function is called a Lagrangian, and to calculate first derivatives with respect to every parameter. We have here two parameters, b and lambda, and we should assume that these derivatives are equal to 0. It is a general approach. I know that maybe for some of you, are not familiar with this method, but tomorrow we will be talking about similar problems. Maybe not such complex as this problem, but they will be very similar, and then the idea of which we have here, this idea will be very obvious and very simple. How to solve these or similar optimization problems. And when after calculating first derivatives and after assuming that they are equal to 0, we can get this form, this solution. Please look at this expression. It is an expression in which we see some elements, and I think that you remember very similar expression. You remember the first element which we have discussed today. It was about eigenvectors and eigenvalues. You remember this definition. A multiplied by V is equal to lambda multiplied by V. And here we see very similar expression. But instead of A, we have S. V, we have B1, and here B1. And instead of lambda, we have lambda 1. So it is the same form of notation. So we can say that this expression is satisfied by elements which we know. We are looking for values for B, which satisfies this condition. So looking at it, we can say that if we remember that S, it is a matrix, it is a square matrix, because it is a variance-covariance matrix, then if we take an eigenvector of S, then for sure this eigenvector will satisfy this condition. So we should put eigenvector here as B1, and eigenvalue corresponding to this eigenvector here as lambda1. So this equation has only, maybe not has only, but has a solution which is equal to eigenvector and eigenvalue corresponding to this eigenvector. So we see that if we are thinking about the position of this first axis, it should be the same as the position, as the direction of the eigenvector of variance-covariance matrix calculated for our data. And it is the solution, and it is the idea of principal component analysis. When we want to maximize, to find the position of the first axis, for which the amount of information corresponding to this axis should be the biggest, we should find the position which will be equal, the same as the direction of the first eigenvector. And it is the solution for this task. So using eigenvector, we will solve our problem. But we have here discussed only the problem which was related to finding the first axis. Now we can repeat the whole method, the whole procedure, and to use the same approach for finding the position of the second axis. And the position of the second axis will be defined by the second eigenvector. So when we are talking about principal component analysis and about this new coordinate system, this new coordinate system is defined by eigenvectors of variance-covariance matrix calculated for the original data. In using these vectors, we can maximize variances which are related, variances corresponding to every axis. But also we should remember about this second condition. The second condition, which was related to covariances. We want to have all these covariances equal to 0. So now we should check. In this case, we will have covariances equal to 0. But maybe also we will make a short break, and maybe after 10 minutes, we will talk about this problem. How to check if covariances are equal to 0. So we will meet at 6:20. Okay, we can start our last part of our meeting for today. And now we will talk about redundancy, which is represented by correlation between variables. As I said before, we are going to remove this redundancy. We are going to have all covariances. It means also all correlations equal to 0. Here in this matrix, we have covariances. But of course, very often we use that data are correlated. Correlations and covariances are related to each other. If we want to transform covariance value to correlation coefficient, we should divide this value by standard deviations. For example, if we want to calculate correlation coefficient between the first and the second variable, we should take this covariance value between the first and second variable and divide this value by the product of two standard deviations. The first standard deviation, it is a standard deviation for the first variable, and the second, it is a standard deviation for the second variable. So dividing covariance value by the product of standard deviations, we can get correlation. So we are going to check if what will happen with covariance matrix after using eigenvectors as the basis for our data. As it means as directions which we will use for defining axes in our new coordinate system. What will happen with our variance-covariance matrix? So we are here. First, we will be talking about variance-covariance matrix for original data. So we can calculate it. We calculated it in the first part of our lecture, and we remember it was CX object. And we know that we can decompose this matrix using eigendecomposition. So we can present this matrix as a product of these three matrices. So variance-covariance matrix for our original data, after centering, of course, we can present as a product of a matrix with eigenvectors of this CX matrix, multiplied by D. D, it is a diagonal matrix, and as diagonal values, we have eigenvalues. And here, E transposed, it is an eigenvector matrix, or a matrix with eigenvectors. So it is possible to present this variance-covariance matrix for original data in this way. Here, I perform these operations. I have variance-covariance matrix here calculated, so cov function, as I said before. I did not mention the second parameter because there are different formulas for calculating variance-covariance matrix. The difference is related to this value which I will, here we have this formula. So variance covariance matrix is calculated in this way. We should here sum up these products and divide it by n. N, it is a number of observations, number of objects. But for some other purposes, we sometimes want to calculate it in different way and divide this sum by n-1. Because in this case, I want to calculate it dividing by n, therefore I should use this second parameter here. So when I use this parameter here, it means that I'm going to make some changes. I'm going to divide this sum by n. Therefore, we have the second parameter here. So we have this variance covariance matrix calculated here. I use it here and perform and calculated eigenvectors and eigenvalues. They are here. After it, I sorted eigenvalues and I change the order of eigenvalues because I want to have them in descending order. Corresponding changes also I perform to eigenvectors. Also, I change column in this matrix with eigenvectors. So all these operations are defined here. After it, I created this diagonal matrix D, because you remember, we have a vector with eigenvalues. So now I created this matrix and I tried if everything works in the right way. So we see here a variance covariance matrix, and this matrix is here. And here we see a matrix which I obtained using this decomposition. It is here. Please compare these two matrices. They are the same. So, of course, our decomposition works for our variance covariance matrix. So it is variance covariance matrix for our original data. For our original data, and we see that variances are here and covariances are here, and covariances are not equal to 0. And it is our problem. So data are correlated. Values of the first and the second variable are correlated. And we want to remove this correlation. We will try to do it here. So we remember that we used our transformation. We use a linear transformation, and we are going to use a matrix with eigenvectors as a description of our transformation. So we use, generally speaking, this P matrix. We are going to perform these calculations here to transform X data, original data, using P matrix as a matrix defining a transformation, and I'm going to find coordinates of these objects in this new coordinate system. And these values I'm going to have in this matrix Y. So I'm going to calculate now variance covariance matrix for our new data. It is here. Our formula for calculating variance-covariance matrix is here. It is very simple because our data are centered. Because without centering, we should have here y minus average value of y. But here it is not necessary because data are centered. So this formula is very, very simple. And y, it is a coordinates of our data set in new coordinate system. Y is defined here. So I use this definition here. So I replace y by px, and here y after transposition is here. I perform this operation, this transposition operation, when I'm going to transpose the product of two matrices. I can move this T symbol, T means transposition, to every element and omit these parentheses, but in the same time, I must change the order of elements. Therefore, here I have not px, but xp with this T symbol of transposition. So we have this form. After it, I can move this element here, this 1 divided by n. So here we see this element, and it is a definition of variance-covariance matrix for our original data. So it is here. So I see that I can present variance-covariance matrix for our new data using this formula. And now we may replace P with this matrix E, in which we have eigenvectors, because we are going to use eigenvectors as a definition of our new coordinate system. So we can replace P with E matrix. Here we see it here. And after making some calculations, we have this form. After it, here, we see this product, E multiplied by E after transposition. But we know that matrices in which we have eigenvectors are orthonormal. So it may be replaced by the product of these two matrices. So we can change transposition to inverse of this matrix. And this is always equal to identity matrix. Identity matrix, when we are thinking and talking about calculation the product, has no impact on the result. So we can remove these elements and these elements. And finally, we have only this dx matrix. So after making all these calculations, we can say that variance-covariance matrix for new data has this form. This form dx. dx, it is a diagonal matrix in which we have eigenvalues calculated for variance-covariance matrix calculated for original data. So we see that these values, which we have here, have a form about which we were talking here. So we know that this variance-covariance matrix is equal to D matrix. It means that it has variables here, values which are not equal to 0 here. They are in descending order. Therefore, I want to have values, eigenvalues in descending order. And we know that these values are equal to, so we know that variances are equal to eigenvalues calculated for variance-covariance matrix for original data, and we have values equal to 0 here. So data are not correlated. So also we see that our solution fulfills the second goal, which was defined here, that we want to remove redundancy. And we did it, because now we have no redundancy in our new description of our data set, because all covariances are equal to 0. Because we have values which are not equal to 0 only on main diagonal. So all these, our calculations, we can check. Here you see this transformation matrix, which is equal to our matrix with eigenvectors after transposition. And I use this transformation to our original data. Original means after centering. I calculated new coordinates. And here I displayed this matrix. And I calculated variance-covariance matrix for my new data set. It is here. And variance-covariance matrix calculated for this data is here. On main diagonal, we have values which are equal to eigenvalues obtained for variance-covariance matrix for X dataset, and covariances are equal to 0. We have the same situation which we had several times, so we have values which are very small, so in practice you can treat them as values equal to 0. So we see that we achieve all our goals. First, we find directions which assure the maximization of variance. And second, we find directions for which covariances are equal to 0. And all these elements are very, very important when we are talking about principal component analysis. So in practice, of course, we can say that principal component analysis, it is a method which we use for analyzing our data, in which we are trying to find this new coordinate system with these features which I mentioned before. But you see that the mathematical background which we use for it is very, very maybe interesting, and it is very good to know all these elements which works for us when we use principal component analysis. And the last remark for today. I said today that principal component analysis is used for reduction of a dimension of the space in which we describe our objects. We can say it simply, it is a method which we can use when we want to decrease the number of variables. But I did not say about it today. But the method is very simple. We have new coordinate system. And we know that the importance of every variable, which corresponds to every axis, is defined by the variance, which is calculated for projections of points on this axis. And because we have our eigenvalues in descending order, we know also that these variances are in descending order. So if we want to decrease the number of axes, first we should calculate all axes, and we should remove these which are at the end of this list, because the information value of coordinates related to this axis is the smallest. So we should remove these axes for which variance is the smallest. Very often we use only the first and the second dimension because it's good for us to use only two coordinates, because then we can present objects as points on two-dimensional graphs. And I think that all for today. So thank you for participation in our meeting, and we will meet tomorrow. Thank you very much.